have seen many of the properties something like basic from starting from basic definitions to eigenvalues and eigenvectors next, and then vector matrix norm to like concept something like induced norm, and then we followed up with this linear equation solution and things like that, and ended up with pseudo inverse concept and things like that. Now, we will continue further of some of the topics that are useful in modern control theory in this particular lecture. Okay. So, the first thing that comes to mind is something called matrix transformation. Okay. So, this matrix transformation is the question that we are asking here is something like this. Can we can a matrix, suppose we have a matrix A, can this matrix be transformed into a simplified form, okay, without losing its properties actually. That means, I mean the properties of the matrix, the basic properties of the matrix we do not want to lose, but still suppose a given matrix A I want to transform it to a matrix B such that if necessary I will recover back my matrix A actually from B. Okay, that is the thing that I am talking about actually. And this answer to this question is fortunately yes, and the options that we are having is like similarity transformation and equivalence transformation. Okay, so, these are all things that we will study in this particular class actually. So, what is a similarity transformation first of all? So, if I mean similarity transformation is a concept for square matrices, and equivalence transformation is a concept for non-square matrices as well. Now, definition wise, if A and B are n by n non-singular matrices and P n by n is also non-singular matrix such that this relationship holds good, that means B is equal to P inverse A P, then we call A and B are similar actually. Okay, that is the definition. So, A and B has to be related to each other with this P inverse A P, and all that is necessary is that P matrix has to be non-singular, that is all actually. So, I can really talk about P inverse whenever I need actually. Okay. So, if you do this transformation, let us say we somehow find this P matrix actually and then carry out this P inverse A P, then it turns out that this matrix A can be reduced to like a diagonal form, okay, or in if diagonal form are not possible, then it is a Jordan form we will end up with actually. And then this diagonal form is possible provided this matrix A has n linearly independent eigenvectors. Okay. Remember, A is n by n matrix. So, it can have in eigenvector n eigenvectors, and if this A matrix has n linearly independent eigenvectors, then it will be lining up with the B matrix which is purely diagonal. Okay. Otherwise, if it does not have n linearly independent eigenvectors, which happens provided this some of these eigenvalues of the A matrix are repeated, there can be a chance of getting generalized eigenvector and things like that. Then we will end up with a Jordan form which is very close to a diagonal form, but is not really diagonal form. Okay, we will see that actually. And steps for finding this P is, okay, how do you find out this particular P? The steps are something like this, and find this eigen. First of all, you have to find the eigenvalue eigenvector pair for this A matrix actually. Okay. So, you find the eigenvalues first and then go ahead and find the n linear independent eigenvectors first, and then if the eigenvectors are not possible, you can include generalized eigenvectors. Remember, these are like eigenvectors. So, that means generalized eigenvectors are guaranteed to be linearly independent compared to the regular eigenvectors actually. So, you go ahead and find n linearly independent eigenvectors. Okay. Then you construct a P matrix by putting these eigenvectors side by side actually in terms of column vectors. So, that means if I find let us say V1, V2, V3, then P matrix is nothing but V1 simply I put it in the first column, V2 I put it in the second column, V3 I put it in the third column. Okay, that is my P matrix actually. And really it does not matter what magnitudes you take, because the operation that you see is P inverse A P, right. So, this inverse and P, the P inverse will and multiply by P will take care of that magnitude actually. Not so much concerned about normalizing that eigenvectors actually. If you want, you can normalize, but there is no particular necessity of doing that actually. So, you can simply put the eigenvectors side by side, and if suppose V2 and V3 are not really independent eigenvectors, then V3 can be a generalized eigenvector that we discussed last class actually. Okay. So, that is how we will get the P matrix. Then you construct this B matrix that way, P inverse A P, that is all you do actually. Okay. So, that is what will give us like B matrix that we want actually. Okay. and we will not take a very specific thing, because these things this is just a review class anyway. So, it is not a matrix theory class per se. So, some of these things I will assume that okay, you can find suitable examples from textbooks actually. And let us say some of the properties, very useful properties rather. Then if a matrix is symmetric, that means A equal to A transpose, then there exists an orthogonal matrix P. Remember, orthogonal matrix means inverse is transpose, that means P transpose P is equal to identity. So, what it tells, if a matrix is symmetric, then there exists an orthogonal matrix P whose columns are normalized eigenvectors of A, right, such that B equal to P transpose A P. You do not have to talk about inverse anymore, remember that, because P inverse is P transpose anymore, I mean P inverse is P transpose in this case. So, B is nothing but simply P transpose A P. So, that the algebra is much simplified actually. So, that happens if you have a symmetric matrix actually. Remember, just by having a symmetric matrix, you have such a beautiful property actually, right. If you have a symmetric matrix, then it is guaranteed to have n orthogonal eigenvectors, and then the P matrix will turn out to be orthonormal, I mean orthogonal, because if you put that eigenvectors, you normalize that. So, remember a orthogonal matrix, the columns of the orthogonal matrix needs to be orthonormal. So, in this case you need to formulate a matrix P with the components of P, that columns of P should be orthonormal to each other. So, that means eigenvectors has to be normalized first actually, normalized eigenvectors, remember that. So, once you normalize the eigenvectors, put them side by side, formulate the P matrix, then P transpose is a P, that is all you have to do actually, you do not need further algebra actually. All right. The next property is A is similar to a diagonal matrix if and only if A has linearly independent eigenvectors. Okay, remember that is the thing what you are talking about. Okay, I mean we are always watching out, looking out for whether you can really reduce it to a diagonal form, because that is the simplest form that you can have actually. So, that is possible, okay, if and only if this A matrix has linearly independent eigenvectors actually. Okay, it is not dictated by eigenvalue condition, it is dictated by eigenvector condition actually. Okay, if a matrix has n linear independent eigenvectors, then it is possible to have. Remember, if the eigenvalues are non-repeated, it is guaranteed to happen. If it is repeated, then there is a chance that it can still happen. Okay. And then there is a chance that it may not happen. I mean, so the real requirement is that you should have n linearly independent eigenvector, that is the real requirement actually. The third property, if A has n distinct eigenvalues, obviously that is what I just told, the non-repeated distinct eigenvalues, then A matrix is guaranteed to have n linear independent eigenvectors, and hence by this property too, it is similar to a diagonal matrix. Okay. And on the diagonal it will contain eigenvalues actually. The diagonal matrix, that the B matrix is guaranteed to be diagonal, but the diagonal matrix is nothing but the eigenvalues actually on the diagonal. Okay, what you have in the diagonal elements, the same eigenvalues will pop up actually. Okay. So, even without carrying out this algebra, you can simply tag what is B actually. Okay. If you simply find out the eigenvalues and the similarity transformation, you do not have to do all this algebra, you simply tell okay, that is my B matrix actually. Okay. All right. So, similarity transformation we will continue further discussion. So, what it tells us? It tells us that having n distinct eigenvalues is only a sufficient condition, right. The necessary condition is actually L linear independent eigenvectors. If you have linearly independent eigenvector, n of them, that is actually the necessary condition, and this actually it comes from the sufficient condition, because if it has n distinct eigenvalues, then the other one is guaranteed actually, and hence it is the result is very obvious actually. 0 0 0 and then 0 1 0 0 0 and then 0 0 1 0 0, all those vectors are actually linearly independent of each other. They are all orthogonal to each other as well as normal. So, that entire identity matrix is actually a orthogonal matrix actually. Okay. So, what does it tell you? Having repeated eigenvalues does not necessarily guarantee that the eigenvectors are linearly independent actually. It can be linear independent, it cannot, it need not be actually. And now the next question is, if the matrix is of full rank, that means the rank of the matrix is n, it guarantees that the n linear eigenvectors will happen actually. If you have a full rank matrix, that n by n matrix has rank n, that is actually, that will guarantee that you will have n linearly independent eigenvectors, and hence you can actually reduce that matrix to a diagonal form actually. Okay. Now, the next concept is equivalence transformation. Okay. We will go ahead and see what is equivalent transformation now. See, all this similarity transformation is very nice, and for further examples and all you can see it from the books and all, or I mean this is very apparent from small discussions like this, or further examples you can see that from books actually. Now, the question is, if you have a non-square matrix, rather m by n matrix, okay, then obviously you cannot talk about eigenvalues, eigenvectors. These are all eigenvalue vector pair is good only for square matrices actually. Okay. So, if you have a non-square matrix, how do you reduce that? Okay. Now, actually now we will ask a different question. We will not constrain ourselves to like P inverse AP sort of thing. Okay. So, this we will just tell, okay, this can we multiply, pre-multiply by P and post multiply by Q, another matrix actually, okay, where the condition is P and Q are supposed to be non-singular matrix, and that is all. Okay. P and Q are supposed to be non-singular, that is all actually. So, why that is necessary, also remember that I want to recover my A matrix, I mean from the B matrix also. So, if I have B equal to P A Q, I will recover it by multiplying this P inverse B Q inverse also, right. This will be P inverse P A and Q Q inverse actually. So, that is nothing but A matrix. This is I times A times I, that is A matrix. So, the real requirement here is that P and Q has to be non-singular, otherwise I cannot talk about their inverse here actually. Okay. So, if I take two different matrix P and Q, they are supposed to be non-singular, and then I carry out this algebra P times A Q, then I will end up with B matrix, that is called equivalent transformation. Okay. Now, it so happens that if you really do this algebra and just leave actually, that means P and Q are just non-singular, nothing else actually. Okay. Then it so happens that you reduce it too much actually. That means the reduced form can always take you to this kind of a form actually. You will simply have, let us say the matrix has rank R, then you will left out with an I matrix, identity matrix R by R, and all other elements of that matrix B is going to be 0. So, okay, that does not contain too much of an information actually. So, I do not want to lose too much of information by doing so much of, by bringing in so much of flexibility actually. So, and if that is the case, okay, I want some diagonal elements to pop up, some elements to be there instead of identity here, okay, and I can do that by constraining this P and Q little more actually. The only constraint right now is that P and Q are non-singular, but let me constrain a little more and ask, okay, can I now talk about something like a orthogonal P and Q basically. Okay. Okay. So, if I talk about an orthogonal P and Q, okay, then that is going to happen actually. Okay. So, that means let us see little down the line, if orthogonal P and Q means what? It is P inverse is P transpose and Q inverse is Q transpose. So, instead of talking about just a non-singular matrix, I will talk about orthogonal P and Q also. Then it will happen that these diagonal elements are no more 1, some numbers will pop up, and those numbers are nothing but what are called as singular values actually. Okay, we will see that slightly down the line. So, that takes us to singular value decomposition, and this singular value decomposition SVD popularly comes short form, and in fact MATLAB has a SVD command also by the way. If you give a SVD and within brackets of matrix, that will give you a singular value decomposition, it will give you both P, Q and then B matrix, everything it will give you actually. Okay. That is the command in MATLAB also by the way. So, what is it actually? The singular value decomposition is a special class of equivalence transformation where P and Q matrices are restricted to be orthogonal. Okay. That means P P transpose equal to Q Q transpose equal to identity, but you can do that really actually. Okay. So, you have to write P P transpose equal to I and Q Q transpose equal to I. I cannot make them equal to, that this is no more equal to each other, because the dimension of P and Q are not same. So, that the I matrix that you are talking here and the I matrix you are talking here are of different dimension. So, individually they are okay, but I cannot make it equal to here actually, just keep that in mind. Okay. Anyway, so if I constrain these matrices P and Q, P P transpose equal to I and Q Q transpose equal to I, then the reduced form that I get actually is nothing but a singular value decomposition, and then we will see that actually in an example also. Okay. So, what it tells us actually under an orthogonal equivalence transformation, okay, orthogonal equivalent transformation, we can actually achieve a diagonal matrix provided we start with a diagonal matrix actually. Okay. So, this particular thing is actually in general it can be a non square matrix. Okay. This is the reduced form is m by n actually, the dimension remains same per n v anyway. Okay. So, if I really have to do that, then if I start with a diagonal, I mean if I start with a square matrix, then actually we can go ahead and reduce it to a diagonal form also by singular value decomposition. We really do not have to do this equivalence transformation, you can also do singular value decomposition for square matrix as well. Okay. This is more general concept actually. Okay. So, under an orthogonal similarity transformation however, okay, we can achieve only a triangular matrix, which is that is called as Square's theorem actually. Okay. Remember, similarity transformation does not constrain this as orthogonal matrix, right. This, like it happens only when there is a I mean this is a symmetric matrix basically. In general it is not symmetric, we do not talk about an orthogonal matrix here actually, right. We just simply talk about a matrix which is something like P inverse A P, that is all we talk about that, not more than that. But here we talk about more than that, and we will talk, we are actually constraining P and Q to be orthogonal matrix by purpose actually, we are just doing that purposefully. Okay. But if you do that also in the similarity transformation, that means in that whatever you are talking this B equal to P inverse A P, in that you constrain P to be orthogonal actually, okay, this P is to be orthogonal, then what happens is in general you may not be able to find a diagonal matrix actually. Okay. That happens, you will still be able to find a diagonal matrix provided A is symmetric, in that case probably yes, but in general it is not. Then in general you will find, okay, this B matrix will happen to be a triangular matrix actually. Okay. So, in general you can go to a triangular matrix, but not more than that actually, just keep that in mind actually. Okay. All right. Now, let us say let us define singular values formally, okay, and singular values can be defined something like this: positive square root of eigenvalues of A transpose A if A is real, and there is a equivalence if A is complex. Most of the time in control theory we will deal with A is real matrix anyway, okay, but in general if A is a complex matrix, then you can also define something called A star, which is like complex conjugate transpose. This is simply transpose, but this is actually complex conjugate transpose. Okay. So, concepts are very parallel. Suppose whatever you do with A transpose, almost the similar thing you can carry out with A star actually. Okay. That is why this the definition and everything will go parallel, hand in hand actually. Okay. And also remember that if A transpose A is positive semi definite, and similarly A star A is also positive semi definite, guaranteed actually. Okay. Those are generalization of concepts from real to complex domain actually. Okay. Let us confine ourselves to A transpose A only, and so that the singular value is nothing but eigenvalues of A transpose A and square root of that actually. Okay. So, both A transpose A as well as A star A are positive semi definite for sure actually, that we have shown that before actually in the previous class. And if it is positive semi definite, their eigenvalues are guaranteed to be greater than equal to 0, they are guaranteed to be either 0 or positive numbers actually, and hence I will never land up with a complex value as a square root actually, because what is inside here is either 0 or a positive number. Okay. So, I have a choice of taking a plus or minus here, but I will simply consider the positive quantities and tell that that is my singular value actually. Okay. So, that is the singular value definition. Okay. So, as I told, for singular value computation only positive square roots are needed actually, the negative square root you can neglect probably. Alright. So, once you do this, then this PDQ whatever you discussed, the D part of it will happen to be diagonal, okay, where in the diagonal you do not have 1 1 1 anymore, but you have sigma 1 sigma 2 up to sigma r now. Okay. If the matrix is of rank R, then the exists orthogonal or the orthogonal matrix is closely related to unitary matrix in complex domain. So, if you take a P transpose equal to identity, then they tell okay P star is also identity, that is in that sense it is called a unitary matrix in general. Okay. Well, no, let us not worry about that anyway. So, there exists an orthogonal matrices P and Q such a way that A is equal to P D Q, where D is nothing but this structure, where the first square matrix of R by R matrix, the diagonal entries will happen to be singular values actually, rest of all other elements will happen to be 0. Okay. Now, the question is how do we find this P and Q again. So, remember similarity transformation, we had a procedure to find P matrix, we just took the eigenvectors, put them side by side and got that P matrix. Now, how do you find P and Q matrix, both the matrix needs to be found out here actually. So, here is a procedure, how do you find that. So, first we find out the eigenvalues and eigenvector pair for this matrix A transpose A, remember that. This is see the definition wise it is actually eigenvalues of A transpose A, it is not eigenvalues of A only. Okay. So, we have to find out the eigenvalues of eigenvectors of A transpose A, that is the matrix actually. Okay. Now, obviously by definition the singular values of A are nothing but the square roots of these eigenvalues, right, that is obvious from the definition actually. Okay. So, this this sigmas or the singular values I can find out simply from definition. Okay. Then you can order this sigma such that okay, this remember A transpose A is going to be something like an n dimensional vector actually. So, you can have a bunch of zeros and a bunch of non-zero values, and the zero values are not singular values by the way, by definition only positive numbers are singular values, not zeros actually. Okay. So, you arrange that okay, tell okay, first R elements are strictly greater than 0. So, those are the singular values and rest of the values are actually 0 0 0. So, I will just order them that way. So, that is just for convenience actually. Now, the question is how do you find this matrices P and Q still, I mean that we did not discuss yet. So, now let us construct these y vectors y1 y2 up to yr this way 1 by sigma I into A times xi. Remember xi is the eigenvector for this matrix actually, this A transpose A. So, that is also we are having that by now. Okay. So, each of the eigenvectors if I just normalize that by dividing it by the corresponding singular value, then I will get this is remember A times that vector is also another vector, and then I multiply that by 1 by sigma I will get another vector. So, that vector I will construct y1 y2 y3 up to yr, and then tell okay, that those y1 to yr I will put them together with further expansion actually. Okay. How do I expand that? So, y1 to yr is available in this series, okay, and I cannot do the similar algebra for rest of the thing because rest of the things are 0 basically. So, I cannot divide it by 1 by 0 and all that is not possible there. So, but I still need an m dimensional vector actually, right. So, up to y1 to yr I already have. So, I have to expand this series or extend this basis vectors what we call for further dimensions. Okay. So, that is possible actually. I will give an example how do you expand and all that actually next. So, y1 to yr is there. So, yr plus 1 yr plus 2 and all that will construct that. I mean it is possible to expand. So, that these vectors will be orthonormal to these rest of the values actually, remember that. So, these columns whatever columns we will need to put it later, all these columns needs to be orthonormal to each other because P needs to be orthogonal, remember that. So, the column vectors has to be orthonormal to each other. So, using that condition I will be able to expand this vector up to m dimension actually. Then my P matrix is given by that and my Q matrix is given by that actually, because remember x1 to xn is already available by this eigenvalue eigenvector it is already available. So, Q matrix is already there and P matrix is constructed that way. Okay. And all that will be done for you by MATLAB command SVD inside that actually, that routine whatever is available that will be doing this. But it is also good to remember or understand what that command is doing actually. So, this command is actually doing all sort of computations behind this algorithm actually. Let us see an example to make our ideas clear. We start with a 2 by 3 matrix. Remember, this is not a square matrix, it is a 2 by 2 matrix, simple square 2 by 2 matrix. So, first step is to construct A transpose A. So, we will construct A transpose A, happens to be like that. Okay. Very quickly you can verify A transpose A, so remember it is 2 by 3. So, A transpose is 3 by 2, 3 by 2 into 2 by 3 is actually 3 by 3. So, hence it you are getting 3 by 3 actually. So, on the eigenvalues of that, eigenvalue eigenvector, if you do that analysis, I mean that characteristic equation and all that, lambda I minus this A transpose A, then take determinant, make it equal to 0, then we will find out that the eigenvalues are nothing but 4 0 0, and here, and obviously these are all kind of greater than 0, all these numbers, because A transpose A is guaranteed to be positive semi definite, and you can see that from the eigenvalues also. Okay, either the eigenvalues needs to be 0 or they are positive numbers, and here it is actually. So, what is my singular value? My singular value is square root of 4, that means my 2 is one of my singular values, okay, and that is it actually, that is all I have. And why is that? Remember, this rank of the A matrix is actually 1. If you see that the first row, if I multiply by minus 1, I get the second row. So, these two rows are not really linearly decoupled, they are linearly dependent actually. So, that means the rank of the matrix is 1 here. So, I get only one square matrix, I mean one singular value actually. Okay. So, after I get this 4 0 0, I carry out this eigenvector analysis and tell, okay, for lambda equal to 4, I have this eigenvector, and all these are normalized by the way. We require that to be normalized, because these are all vectors of the column matrix Q. Okay. So, this column matrix Q need to be kind of orthonormal to each other, remember that. So, each of the vectors needs to be normalized also there. So, I find out this eigenvector, normalize that, find out this eigenvector, normalize that, and find out this eigenvector, normalize that. And here is an example, you can see that even though lambda is repeated 0 0, you will still be able to find out these two eigenvectors separately, I mean linearly independent to each other, and each of them are normalized. So, each of them are actually orthonormal to each other. So, by finding out this x1 x2 x3, I already get my Q matrix that I require later. Okay, x1 x2 x3, if I simply put them together and take a transpose, this transpose is essential by the way. Okay. You have to put them as either a row vector sense, or you put them as column vectors and finally take a transpose. That is my Q matrix actually. Okay. So, there is a transpose here by the way. All right. So, that is I found out x1, x2, x3, then I put them together and then took a transpose. So, my Q matrix is ready. Okay. Now, I go back and see what to do with the P matrix actually. All right. So, here is a 4 lambda 1. So, my sigma 1 happens to be square root of lambda 1, that is 2. Sigma 2, sigma 3 are actually like 0 0, I mean singular values are 0 0. So, they will not play much of a role here actually. Okay. So, what do you talk about that actually? Some by the way, some definitions, some books will tell that 0 0s are not singular values also. So, they are simply written like sigma 2, sigma 3, does not mean they are singular values actually. Okay. So, anyway, coming back to that, this y1, okay, is actually 1 by sigma 1 times Ax1 by that procedure. Remember that procedure you have to carry out now, this one. Okay. Right. So, sigma 1 is non-zero. So, we can get y1 like that. Okay. So, y1 is straightforward, 1 by sigma 1 into A times x1. So, I will carry out this exercise, I will multiply A times x1, then take out 1 by sigma 1. Okay. So, this is A matrix, this is 1 by sigma 1, this is A times x1. Okay. And finally, I will end up with this vector actually 1 by square root of 1 minus 1. So, this is all about y1. So, what about y2 now? So, we have to extend this y1 to y2 in such a way that y2 will be orthonormal to y1, that is the condition actually. So, let me start with y2 as AB column wise. So, I put a transpose here actually. So, that means A and B are column wise next to each other actually. So, I find y2 in general such that y1 and y2 will be orthonormal. So, that means what? The inner product between them is going to be 0 and the inner product between y2 and y2 has to be 1, that is the condition actually. Okay. So, if I y1 and y2 inner product, if I carry out, that is A minus B, which is equal to 0, and inner product of y2 and y2, that is y2 transpose y2 and things like that, that is A square plus B square is equal to 1 actually. So, I have to satisfy these equations, that means a minus b has to be equal to 0 and a square plus b square should be equal to 1, and a minus b equal to 0 means a is equal to b. Okay. Now, I put it back here, then it tells me that 2 a square equal to 1 and hence a is nothing but 1 by square root 2 basically. So, obviously, b is also equal to that. So, a and b are equal to 1 by square root 2, that means y 2 is nothing but 1 by square root of 2 1 1 actually. So, I had y 1 okay, like this, and I extended that y 1 to y 2 such that y 2 is orthonormal to y 1, and in that process I got y 2 actually. So, now I have P matrix is y 1 and y 2 which is given like this, and Q matrix already I have actually. Okay. Now, if I carry out that algebra P D Q sort of thing, then D turns out to be only sigma 1 and everything else is 0 actually here, and sigma 1 is 2, and you can clearly verify that P D Q. If I do this algebra, this is my P matrix, this is my D matrix what I am proposing here, and this is my Q matrix, and if you do this algebra it naturally turns out to, I mean very nicely it will turn out to be A. And I mean in my suggestion for your, if you do some exercise in the exam and all that, then I mean just verify this equation one time at the end. If that happens to be there, then you are safe actually. So, what is summary of transformation? If you see this, there are many things that we talked actually. So, a matrix in general can either be square or non-square, right. If you have a non-square matrix, okay, you can actually you can reduce it to semi-diagonal form only. Okay. Semi-diagonal form is that form that we discussed about this at the beginning itself, right. We discussed about this form, the I being there in the main diagonal actually. Okay. So, either you can go that IRR in the main diagonal, that is a semi-diagonal form, or you can extend that and tell okay, hold on a second, we can actually go ahead and carry out singular value decomposition. And this has actually a lot of meaning, because many of the numerical methods, by the way, the conditioning and other thing, whether your numerical algorithm is well conditioned or ill conditioned, things like that, they also come from something called condition number, and condition number is nothing but maximum singular value divided by minimum singular value. So, singular value is not just about matrix transformation alone, there are a lot of uses for numerical methods as well actually. Okay. So, that is about non-square. So, if you have a non-square matrix, you have only this singular value decomposition primarily as your I mean some sort of a weapon for reducing the matrix actually. Now, what about if you have a square matrix? Okay. Now, that will arise two different cases, either I have a symmetric matrix or I have a non-symmetric matrix. Okay. Now, if I have a non-symmetric matrix, I can directly go ahead and apply this Squar's theorem and tell okay, well I can restrict my P matrix to be orthogonal, then I will end up with a triangular form by orthogonal similarity transformation basically. Instead of that P inverse A P has to be orthogonal as well, then I will end up with triangular form. Or I can actually go ahead and do this orthogonal equivalence transformation, like what I do here for non-square matrix. I will also do that same thing here, and I will end up with still a diagonal matrix actually, right. But in the diagonal I need not get if I do it that way, in the diagonal element I will get singular values actually. Okay. Now, what if the matrix is square and symmetric? It is square as well as symmetric matrix. In that situation, it can have n linearly independent eigenvectors, or it need not have that. Okay. And if it has n linearly independent eigenvectors, I can reduce it to diagonal form by similarity transformation, where the diagonal elements are nothing but eigenvalues, or if that is not possible, then I will end up with Jordan form by similarity transformation. And what is Jordan form? Jordan form consists of let us talk a little bit about that. What is Jordan form? The Jordan form is something like J, okay, which will talk about block Jordan form actually, J1, J2, okay, block diagonal matrix, where these are this J1, J2, J3 like that are actually Jordan blocks actually. And what is that? Let us say J2 stands for lambda 2, which is repeated twice. Then if it does not have two different eigenvectors, then I will end up with okay, this lambda 2 is let us say 1 actually. So, then you will end up with 1, okay, 1 is not a good number probably, okay, I will take let us say 4, okay, lambda 2 is actually 4, then corresponding j 2 will have 4 4, then it will have 1 here and then 0 here, it is not 0 actually there. So, this particular thing what you see there that okay, this particular thing is not 0 actually, that is 1 here actually. Okay. Now, if you have let us say j 3, okay, lambda 3 is okay, lambda 3 is equal to let us say 7 or something, but it is repeated thrice, let us say 7 7 7 sort of thing, then corresponding j 3 will have 7 7 7 here, and obviously these are all 0 0, the below side of it. The above side it will have 1 here, okay, and 1 here and then 0 here. So, you have this 1 is coming up just above the diagonal, sorry, this is not true actually. Okay. So, you have 0 here and you have this is the diagonal thing, okay. And similarly, this is the diagonal 7 7 7 and then there will be a 1 actually. Okay. And remember, if j 1 this lambda 1 it happens to be 2 and then it is just I mean kind of it is repeated still, but you have sorry, it is repeated, okay, but you have linearly independent eigenvector for that. Then the corresponding j 1 will have the corresponding j 1 will have simply 2 2, okay. This 0 will happen here, okay. That means still it is a diagonal matrix actually. So, if you put them together, your j matrix will turn out to be a very big matrix, and then okay, that is first one is 2 2 anyway. So, I will not worry about that, that is my j 1. Then the second block thing will be having like 4 4 1 0, and the third element will have 3, that is like 7 7 7, okay, then 1 1 here, then 0, and everywhere else it is 0 anyway. So, that is the Jordan form that you are talking about actually, okay. So, that is in general you will be able to do that actually. Alright. So, this is the summary of what it tells, okay, if I have n independent eigenvectors, I will end up with a diagonal matrix, or if I do not have n independent eigenvectors, I can end up with a Jordan form in general, and this is actually a generalization form over this actually, okay. And if you really want a Jordan form, then that is where your generalized eigenvectors will lead you to Jordan form actually, okay. If you have regular eigenvectors, it will lead you to diagonal form, and diagonal form is also like a special Jordan form, you can say that way, because if you have a diagonal matrix per se, okay, something here, something here, something here, and each of that is also a Jordan block actually, okay. Okay. So, a diagonal matrix is also like a Jordan matrix in general actually. So, you can say that way, okay. Alright. So, this is all about transformations actually. So, summary of transformation talks about that. So, first you have to see whether you have a square matrix or you have a non-square matrix. If you have a non-square matrix, options are limited, we are just talking about a singular value decomposition. If you have a square matrix, you can have a non-symmetric square matrix or a symmetric square matrix. If you have a non-symmetric square matrix, again your choices are not very high, okay. But if you have a symmetric square matrix, you can see the beauty actually, like you can have like n independent eigenvectors, and then you can doesn't have n independent eigenvectors, and then you can have diagonal form, non-diagonal form, in Jordan form, like that actually you can talk. Okay. Anyway, so these are all the transformation actually. Now, let us talk about a different concept altogether, and that is what we will need in control theory also many times. So, here is a concept which we call as the vector matrix calculus actually, okay. So, what we are doing here? We are talking about taking calculus further into the vector matrix domain actually. We know what is differentiation, we know what is integration in a scalar sense actually. Now, if in a vector sense what is happening, in a matrix sense what will happen, okay. And remember, most of the time we do talk about, I mean without even bothering for that, we talk about x dot equal to ax plus bu, many times we see that actually, okay. So, what is x dot after all? X dot is nothing but what x dot you see here is something like that, what you define here. So, that is nothing but x1 dot, x2 dot, x3 dot, okay. So, if I have x's like this, x1, x2, x3, which are all time varying, okay, let us say, and time is just a free variable, you can just assume that is some independent variable, and the derivative is with respect to that actually. So, if it is t here, which is very common in dynamical systems anyway, then we talk about x dot or dx by dt actually. So, by definition what we do here is, if you have x1, x2, x up to xn, then by definition x dot is x1 dot, x2 dot, x3 dot, like xn dot, simply by definition. Remember, these are all column vectors. I have just put them row by row and then made a transpose actually here. These are all column vectors actually. That is a default. Default notation is column vectors in control theory. Okay. So, if you similarly, if you talk about integration of a vector, okay, then all that you have to do is element by element integration. So, differentiation is element by element differentiation, and integration is element by element integration. That is all you do actually. Similarly, if you have a matrix which is time varying, okay, then you can talk about differentiation of that. A dot is nothing but element by element differentiation all over, and integration is element by element integration all over. Okay. And then it turns out, okay, some of the useful results which will tell, okay, what will happen if I have d by dt of a plus b, then it is very clear that it will have a dot plus b dot, simply from definition actually. If I have a dot something like this, a is something like this, b is something like that, right, then I can d by dt of a b, okay, let us probably do that very quickly, that is rather easy actually. Okay. Okay. So, I have a matrix something like A11, A12, or let me take a 2 by 2 for example, A21, A22, and similarly B matrix which I have B11 and then B12 and B21, B22. Okay. Then A plus B is nothing, they are all time varying elements, remember that. Then A plus B is nothing but A11 plus B11, A12 plus B12, A21 plus B21 and A22 plus B22. Okay. So, if I talk a dot of that, then this is actually d by dt of this quantity a plus b. So, this is nothing but d by dt of the whole quantity I can divide into that. So, this is a11 dot plus b11 dot, then a21 dot plus b21 dot, okay, and then a21 like that actually, all that thing I can do. Okay. Then I can decompose that and tell, okay, I can take out this and then tell, okay, this is a11 dot, a12 dot here, a21 dot, a22 dot, plus, okay, this plus b11 dot, b12 dot, okay, b21 dot and b22 dot. Okay. So, then this is nothing but, okay, by definition I take out this derivative one outside again and tell, okay, this is nothing but d by dt of a matrix plus d by dt of b matrix. So, this is nothing but a dot plus b dot. So, simply from definition we will be able to show that I mean a plus b dot rather, okay, this is actually what we started with, is nothing but, okay, this quantity is actually d by dt of a plus b. Okay. So, this d by dt went inside, okay, this d by dt went inside of that, okay, then you talk about okay, derivatives everywhere, then you separate it out and tell, okay, this is nothing but a dot plus b dot actually. Okay. So, simply from definition we will be able to show this actually. Okay. All right. Now, go back to that and then tell, okay, further these are simply definitions anyway. So, they are some of the nice results which will tell me that, okay, a plus d by dt of a plus b is nothing but a dot plus b dot actually. So, we use that many times implicitly also, I mean, this is true. Now, what if there is a multiplication? Obviously, these matrices have to commute, I mean, this multiplication should be well defined actually. So, you know how these matrix multiplications are there. So, if A is m by n, then this has to be n by p somewhere. So, the multiplication has to be like m by p after all actually. So, this particular thing in a scalar sense you can already see that if A and B are scalar, then that is the result. Okay. So, it is also in general true for vector multiplication, I mean matrix multiplication in general. Okay. And the only thing that we need to keep it in mind is that the sequence of multiplication should be preserved. You cannot write a dot into b is not equal to b into a dot, that is not true in general. So, the sequence of operation has to be preserved actually. Okay. Then this result is also true. Again you can do that longhand multiplication in general, you take a11, a12, a13 like that up to m by n, then correspondingly you take b, then you apply the definition, then it will go element by element derivative, then element by element it will pop up that way, then you take out and then ultimately you will combine them like this actually. So, it is not very difficult to show from simply definitions and elements actually. Now, here is an interesting thing, okay, which tells me that the derivative of the inverse of a matrix A is nothing but negative of A inverse dA by dt into A inverse actually, right. So, it is very close to what I take it to, suppose I have a scalar quantity, then the d by dt of, okay, this is nothing but x inverse A, that means 1 by x t, let us say, if it is a scalar quantity. Then we know for sure that this is actually x minus of x dot divided by x square actually, right, all are time varying by the way. And similar thing you see here, but I cannot see it the 1 by terms and all I cannot write it there. So, what turns out is very close to what we know for scalar actually. This is for scalar and this is actually for matrix calculation actually, and we can show that not very, I mean the proof is not very difficult actually. All right, the further results. Okay. Now, we will require some sort of kind of Jacobian matrix and things like that also. So, if f of x is this, now it is actually a function of state, which is actually x is a function of time, remember that. Okay. But in general, we will not worry the time dependence part of it. Let us just simply tell that, okay, I have a function of vector, that means the f is a scalar, but x is a vector. Okay. And it is possible, right. One example is x1 square plus x2 square plus x3 square. I mean, that is if you have x is x1, x2, x3, then the function is what I am having x1 square plus x2 square plus x3 square is actually a scalar quantity, but x is a vector quantity actually. So, something similar to situation I am talking actually. So, x is a vector, but the function of that vector is a scalar quantity. Then what we define is a Jacobian vector, I mean this gradient vector rather here. Okay. So, the gradient vector is defined as something like this. Remember, this is again this is a column vector actually, is a transpose out here. So, how do I define? I just take the partial derivatives del f by del x1, del f by del x2 like that. I simply put them together down by down actually. So, what I mean here is del f by del x, okay, I define as del f by del x1, del f by del x2 like that, del f by del xn, simplified definition actually is a column vector. Sometimes people define it as row vector in some books, but throughout our course we will follow that as a column vector actually. Okay, there are small advantages drawbacks defining whatever way. You have to be just consistent with whatever definition you have actually. So, in our throughout our course we will take it as a column vector, and this is nothing but the gradient vector also, del f by del x is nothing but the gradient vector. Now, in the next case, what if I have a vector function, that means x is a vector and f is also a vector, they need not be of same dimension by the way, right. X belongs to Rn, whereas f belongs to Rm. Okay. So, I have a vector function of a vector actually. Then I can still take the first partial derivatives and put them together in a matrix format, and this matrix is called Jacobian matrix actually. Okay. So, if you have a scalar function, this vector is, it will result in a vector which is called a gradient vector, and if it is a vector function, it will result in a matrix which is called a Jacobian matrix. Okay. All right. Then the next concept, what if I have a scalar function, okay, of a vector, but I take a second partial derivative del square f by del x square. How do I define that? And I can still go ahead and define that this way actually, what you see here. Okay. And also remember that del square f by del x1 del x2 is also equal to del square f by del x2 del x1. That is the standard result from calculus actually. That means this Hessian matrix is guaranteed to be a symmetric matrix. Now, this lecture and previous lecture we have seen very neat properties about symmetric matrix. Okay. Many of these things will be exploited later, in especially these matrices are kind of they will appear in optimization theory. Okay. So, many times it will end up with Hessian matrix and things like that. Now, for sufficiency conditions, and sufficiency conditions is nice to see from second derivative and all, and second derivative happens to be Hessian matrix which is already a symmetric matrix. So, these are all nice properties which will be exploited there actually. Now, further results, some of the results are very useful later. Suppose I have a constant b, constant vector b, and there is x actually. Okay, I talk about taking partial derivative of x with respect to B transpose x, and remember B transpose x is a scalar and x transpose B is also a scalar. If I take partial derivative, it happens to be simply B, and you can just do it by longhand algebra and show that very easily actually. You can simply expand that. B transpose is x is nothing but B1 x1 plus B2 x2 plus B3 x3 like that, and if you take out this partial derivative by definition, it will simply pop up as B matrix actually. Okay, it is not difficult to show at all actually. Okay. And then if you do that, the second result tells us that okay, if I take Ax and then take partial derivative del x by del x of Ax, it happens to be A. Again you can do that by longhand algebra, you can show that actually. Okay. Then I take what if I have a matrix something like this, x transpose Ax, then I will use this property, whatever property I have seen here, okay, something similar to that, okay, and I can generate, okay, I can really end up with this result actually. X transpose Ax, if I just take del by del x, it will result in A plus A transpose times x. And as a corollary, if I have a symmetric matrix and I talk about del by del x of half of x transpose Ax, where A is a symmetric matrix, okay, then whatever, let me generalize that a different matrix just to avoid confusion and all, and that is also necessary later. This is a Q matrix, let us say. Then what is that? This is actually half of Q plus Q transpose, right, Q plus Q transpose times x, and then Q transpose is equal to Q basically, right. So, what do you get? Half of 2 Q x basically, okay, that is nothing but Q times x, right. So, if you have a symmetric matrix, okay, to begin with, okay, Q is a symmetric matrix, then what results in is just Q x, provided there is a half term already there. So, these are the reasons why you see in LQR theory a term something like the linear quadratic regulator theory, when we talk about that, we will see this term as part of the cost function actually, and we will also need a partial derivative with respect to x for what is known as co-state equation and things like that. So, there these algebras will be useful actually, what you see there, and that is what I am telling here. If A is equal to A transpose, then this is the result actually. Okay. Now, further results, okay, what is known as chain rules and all that actually. So, this kind of algebra will encounter in optimal control theory primarily, and some of these nonlinear control theory as well. So, what if we talk about f transpose z now. Now, f is a function by of x, g is a function of x, they are dimensionally compatible, and f is a vector, z is a vector. So, f transpose z is a scalar, and then you can still talk about taking partial derivative with respect to x, and this happens to be like this actually. Okay. And these are all not very difficult to show at all actually, just by longhand algebra it will be able to derive that actually. Now, as a corollary, now if one of the function happens to be simply a constant, that means f of f transpose x is f is nothing but c actually, just a constant vector, then you will end up with something like this. Okay. This just from this result you can derive those corollaries actually. Okay. And if you have a matrix Q in between, like f transpose Q z x, then it will also happen to be something similar to that actually. Okay. You can take Q times g x is some g1 of x or something and apply that actually what you have here, and then you will end up with some formula like that. Further generalization, if you have a matrix now, matrix function of x, okay, and there is a vector u also, then the partial derivatives can also be derived. And why do I talk about all these actually? Remember, we have a special class of functions systems of what is called as control affine nonlinear systems, where you talk about f of x plus g of x times u. Okay, g of x is a matrix actually, by the way. Okay, if you have I mean these are special class of systems, okay, what we will deal with sometime later. Okay, f of x is a vector and g of x is a matrix actually. Okay. So, if you have a control affine system, then a nonlinear system that way, then some of this algebra will encounter actually on the way. So, let us get ready for those things and then tell, okay, these are the results that we will need later actually. Okay. And obviously, I do not want I mean there is not required to be remembered actually, I mean these formulas and all we do not have to remember. However, we have to know all these results, because many of the results will be useful. I mean, we should not be afraid about these results actually. Now, there is a question, further question, function of functions, what will happen actually. So, if I have a function of function, then the results are like either I can have this small function as a scalar and the big function as a scalar as well, or the small function is a vector, the big function is a scalar, or the small function is a vector and the big function is also a vector. That means function of a function. So, the first function is a scalar or vector, the second function can be a scalar or vector. Then I talk about derivatives of that final function, then obviously what comes to mind is chain rule actually, right. Function of a function, if you take derivative, that is chain rule. So, the generalization of chain rule to vector matrix thing is also available, and these are dimensional compatibility sense it will be maintained, but the results are fairly similar to what we already know actually. Just have to be careful about the dimension compatibility, and formally we can show that also, the derivations and all are possible to show that actually. Okay. So, these are all vector matrix calculus actually. So, with that I will probably stop here, and so message here is we will now, I mean these algebras are possible, and we will use that algebra wherever it is necessary actually. So, with that that last class and this class we have seen many of the concepts from matrix theory which are helpful for dynamical system analysis as well as control design actually. So, we will I will come back to this control design concepts in our subsequent classes, and with that message I will stop this actually. Thanks a lot.